Hey guys, so last week we started looking at kinetic theory. Part of kinetic theory was involving us in looking at our ideal gas instead of in terms of bulk properties. We started looking at it in terms of individual particle properties. And one of the big assumptions that we made for an ideal gas is that we went from this naive view that each particle in our gas goes from a velocity v, they all have the same speed and direction. We made it more realistic and started talking about them having a random, if you like, stochastic distribution of speeds and directions, which we called CMS. So CRMS is sort of our averaged. We can't speak about individual particles. We can only speak about an average. So actually one of the things that we looked at last week was that PV is equal to a third NM mean speed squared. So this was reworking our ideal gas in terms of statistical properties, if you like. So just to recap CRMS, that's RMS, which means root mean squared. So CRMS written more fully looks like this. It's the root of the mean of the square speeds. So even more explicitly, actually, what we can say is this is the square root of all of the square speeds. So let's say we have n particles in our distribution. That's going to be the square of all of those individual speeds all the way up to the last one, which is n, and then divided by how many we have in total. So that's our CRMS. Incidentally, this is our CRMS squared, so this is equal to CRMS squared. So we had that. And we now know that we can relate some bulk properties here to our sort of microscopic properties over here. So mass of individual particles, the average square speed, the number of particles we have, which is quite useful. And what we want to start looking at is how does that work for particle energies. So we might want to look at, if we have this distribution of particles, what then on average is the average kinetic energy? Now to do that, we need to first look at what kinetic energy is. So your sort of kosher original kinetic energy is just a half mv squared, where m is the mass of our particle and v is the velocity that it has at a given time. But now if we go back to our ideal gas, we don't have particles that all have the same speed and direction. So we need to start thinking about this a little differently. So instead of v, we now have a distribution of speeds, and we can only talk about the average. So likewise, instead, our mean EK is just going to be the average speed squared. So that would be CRMS squared, or to rewrite that, that's going to be m mean c squared. So now we have the internal energy of our gas, if you like, which is pretty cool. But really, we don't want it in terms of speeds. It would be nice, so we have this equation now. It would be nice to rework this so we can calculate kinetic energy with something measurable. And we want to do that because really, when we look at this equation, the mean square speed isn't something that we can directly measure. You can't just get out little stopwatches and add up all of these. We want something more down to earth, more measurable. So the way we're going to do that is actually we're going to use this equation up here. We're going to use another equation which we've come across. So basically we're going in reverse now. We're now wanting the mean speed of single particles, but in terms of not microscopic properties but bulk properties. So the easiest way to go back to bulk properties is looking at the two following equations. We have this microscopic equation, So that's micro. And we also have the equivalent for a macro, so bulk properties, if you like. So that was PV is N Boltzmann constant kBt. So that's our macro. By the way, micro means small, macro means big. So what we want to do is we want our mean kinetic energy in terms of something macroscopic again. We're going to use these two equations. So the first thing I'm going to do, if I call this equation 1 and equation 2, I know that I can set these as equal to each other because I've got PV on the left-hand side of both. So doing that gives us 1 over 3 n m c bar squared is equal to n kBt. Now the first thing we notice here is our n's cancel. That's great. And something else we notice is we now have 1 over 3 m c bar squared is equal to kBt. Now this is good because temperature is a bulk property here, so our temperature, that's going to be useful. And something else we might notice is we've got mc squared here, just like we've got mc squared over here. So why not? Let's rearrange this so that we just have mc. So I'm going to multiply both sides by 3. That's going to give me mass times the mean square speed is equal to 3 kBt. So now what I can do is I can literally just substitute this in up here, and that's going to give me our mean kinetic energy is equal to a half multiplied by 3 kBt. So just tidying that up a little bit, we have that the mean EK of a particle in our ideal gas is equal to 3 over 2 kBt. I'll put a box around that. Now this is big. This is big, and it's big for a number of reasons. The first reason is this says that actually our mean kinetic energy for a particle is equal to temperature. So the energy of a particle is proportional to temperature. Now that's probably not that big. It's not going to be knocking you off your feet. That should ring some bells. We know already the hotter a gas is, the more energy there is in the gas. We've just proved it now. So we have some actual proof. What is big though is that this says that mass is not involved here. So the energy of a particle is independent of mass. Which is weird. Okay, so you would be tempted to say, well, before EK is a half mv squared, so there's a mass in there, so this is dependent on mass. It's not anymore. And the reason being is because we saw in lessons that our CRMS is actually inversely proportional to the root of mass. So if we go back to that equation we had before, half m mean c squared, what this is actually saying is, well, if I square both these sides, that's going to get rid of the square root. If I increase my mass, I'm going to decrease my mean c squared, and vice versa. If I speed up my particles, that is the only way I can do that is by decreasing the mass. So these two are so intertwined that it renders mass independent of the energy of a particle. And the last thing we did with this was we said, okay, we know on average what the energy of one particle in our gas is. What about, so if we go back up here, what about the total energy U in my whole gas? So this is related to thermal energy. Remember, thermal energy is just the collective random kinetic energies of particles, so this shouldn't be a surprise. So what we're saying is the internal energy U is equal to my number of particles multiplied by my mean EK. So each particle has a given energy. My total energy is going to be that energy multiplied by how many particles I have, which is pretty straightforward. So that then is going to be 3 over 2 n kBt. So that's our other equation for this. So that's nice. And that's internal energy, really. There's not a lot to say about that, other than, because this is temperature dependent, if I have two bodies in thermal equilibrium, that means their temperature is the same. I can now say, absolutely, they have the same internal energy. They have the same amount of energy inside. And again, that shouldn't alarm anyone, because that's basically what we studied with delta E is equal to mc delta theta. You know, it's the same idea. Okay, so the last thing that we looked at last week, and the final thing I'll talk about in the video, is we looked at our Maxwell-Boltzmann distribution. And from that we looked at the Boltzmann factor as well. So our Maxwell-Boltzmann distribution here looks like this. It's a nice curve that it steeps sharply to begin with, and then slowly tends towards the x-axis for increasing energy. So I'll just label the axis. This is the energy, and on this axis is the number of particles which have this energy, E, over here. So there are a few things that we can do with this that are quite nice. Obviously, the total area under this graph, so mathematicians, if I integrate this, or non-mathematicians, if I counted up all of these squares, the area under this curve is equal to the number of particles in my system. Now that makes sense, because you can think about this as being made of lots of little bars, where each bar represents the number of particles with a given energy. So obviously, adding up all those bars tells me the number of particles that have each energy, all energies, so therefore that's going to be all my particles. They all have some energy. So that was quite nice. Another thing that we could do is we could define something, some points, some arbitrary energy, and we could say that actually the area on this side is equal, on the left side, is equal to the number of particles with an energy which is less than that energy, and on this side that's the number of particles with energy which is greater than or equal to this energy. So now we can split our distributions into sets of particles which have or don't have a certain amount of energy, which was nice. And that brings us on to what we finally looked at, and that was activation energy. So I could call this energy activation energy. We can think about this as being, say, the amount of energy it takes for a particle to actually do something. So a dead common example is, think of a puddle. Let's call that at room temperature, so it's roughly 300 Kelvin, something like that. And this is going to be full of particles, and they will be distributed randomly with energies in the same way that this curve shows. And what we can say is that, well, there might be some activation energy for particles in this puddle to spontaneously evaporate, to escape the puddle. That's going to take some energy, because to do that we know that water molecules have some mutual attraction. Chemists, because of van der Waals force, other way around, sorry, VDW. So there needs to be some energy, okay, in order to do this, to break that bond and one of the particles to zip away and evaporate. Now what we're going to do is we're going to call that energy, so the energy required to do something, in this case evaporate, we're going to call that our activation energy. And I'm going to call that epsilon, so curly E. So I've already labelled that, that's here on our graph. And we can say now that actually we've got this set of particles on the right hand side of that line that can do this process. So this is my number of particles for which the energy is greater than or equal to the activation energy. These guys can evaporate. They absolutely can evaporate, which is good for them. And actually what Boltzmann was interested in is he looked at this curve and he wanted to define a way of saying, well, if I have n particles, I want to know what fraction of those particles can do this process. How many of them can evaporate? So again, mathematicians, what we could do here is we could integrate this curve between EA and infinity. So if I call this a function of energy, you could, if you wanted, integrate this curve between, so that would be f of E, it's a function of E, integrate it with respect to E, and you would integrate that from epsilon all the way up to infinity. Now, because f is a function which has some energy dependence, which is e to the power E, something like that, you could do that in a couple of weeks in maths, but I'm not going to bore you with that, although I'd love to. So all I'll say is that Boltzmann did the maths, and he invented something that he called the Boltzmann factor. And that's a lowercase f. And all the Boltzmann factor does is it tells us the ratio of particles that can do a process. Or in other words, the ratio of particles, that have the required energy. So that, in this case, is EA. So the ratio of particles that can do a process compared to the total number. So mathematically, what he said was F is equal to the number of particles that have energy greater than or equal to the activation energy as a ratio of the total. And what he found, if you do that integral, is that's just equal to E, Euler's number, or Euler's number, sorry, to the power minus activation energy divided by KT. So actually we can see that there's some temperature dependence here, and obviously we'll look at this next week, but if you increase the temperature of your gas, your average energy gets higher. Your average energy will move in this direction, therefore more particles will have that energy. So that's where I'll end today, and what we'll actually look at next week is this definitely temperature dependence here and activation energy dependence, because obviously if your activation energy is lower, more particles will have that energy. And again, if your temperature is higher, your mean energy moves up, so more particles have it. So actually, before I finish, what I should just finish with is something like this. I should talk about what happens when you have a colder gas or a hotter gas. So if I just get rid of a few things on here, tidy this up, we could call this just some temperature T here. So this here is my Maxwell-Boltzmann distribution at a temperature T. I'll call it T0 actually. So that could be anything, could be room temperature, it could be 500 Kelvin, don't really care. But last thing I'll say is if we lower the temperature of our ideal gas, what that does is it changes our distribution to look more like this. So the peak is higher, but the slope is much more dramatic. And so your peak actually shifted to the left and upwards. So what this is saying is most particles now at a lower temperature have less energy. Okay, that makes sense because we looked at this a few minutes ago. Yeah, and it also says that the sort of nice thing you need to look at this is we know the area under a curve is equal to the total number of particles. So what we have to do is, if our curve shifts, our peak is sort of bunched up. So more particles have similar energies, if you like, but we have to lower most of the rest of the curve because we need to keep the number of particles constant, which is really important. And I'll draw it in black, but we can also look at larger energies. So at higher temperatures, so this up here is T is less than T0, we can also look at in black something like this. I'll draw that a bit neater and get rid of all these lines. Whoops, scoot back a bit, get rid of some of these lines. So at higher temperature, our peak is shifted. Try that again. Our peak is shifted to the right. But more particles have these high energies, so our peak is lower and shifted to the right, so our average energy is higher at higher temperatures. Makes sense, they're bopping around more. But we have more particles that can exist in this part of the curve over here at really high energies. Okay, so I think that's it. So just to summarise, this is our Boltzmann factor. And that again tells us the ratio of particles in our system that can undergo a process like evaporation. And what I'll look at next time is this temperature dependence and energy dependence of the Boltzmann factor, not the distribution. So that'll be next time. Okay, have fun. See you later.